All right, can everyone see that? I'll assume yes.
Yeah, you can
So I'm honored to be representing White Dwarf Asteroseismology in this series, and I'm excited to share what I think is a powerful method to characterize fundamental white dwarf properties by combining precision data from Gaia and TESS on pulsating white dwarfs. Gaia is obtaining astrometric solutions for billions of stars and has been used to identify the largest sample of white dwarfs to date. And TESS is a photometric transit survey that is obtaining nearly uninterrupted month-long light curves of essentially all bright white dwarfs with a 2-minute cadence. So while I expect most of this audience is familiar with the basics of white dwarfs, I do want to highlight two areas where there are outstanding problems to be improved upon. One of these is the spectroscopic technique, one of the most widely used methods for characterizing white dwarf stars, whereby the shapes of observed absorption lines are fit to atmosphere models to acquire effective temperatures and log surface gravities. You've probably seen figures like this very often, where very good fits of models to the data can be achieved. However, there are a few reasons to suspect that results of this method suffer some systematic uncertainties. For one, the line broadening physics are constantly being improved upon, and the results change in response. Some discrepancies between observations and theory have motivated these corrections to be applied based on 3D convection simulations, but that doesn't solve all discrepancies yet. And in addition, benchmark laboratory astrophysics experiments taking place at Sandia National Labs have revealed that current line broadening models fit to different Balmer lines, measured under controlled conditions, yield discrepant results. And finally, intrinsic errors from observational systematics usually dominate over, those are extrinsic errors, usually dominate over intrinsic uncertainties based on the quality of the model fits. I recommend anyone who consumes these spectroscopic fits to be familiar with Josh Fuchs' thesis. He looked at 10 different observational factors that introduce systematics, including things like where you normalize the continuum, what you're seeing is, what various other decisions about the observing process. I also want to mention a couple of challenges for interpreting white dwarf pulsations that are relevant to this work. So this is the spectroscopic parameter space of log G effective temperature, showing the different classes of pulsating white dwarfs that could be studied with asteroseismology. The promise of asteroseismology is to reveal the white dwarf's interior structures, including masses of stratified compositional layers, as well as the chemical profile of the core. However, this potential is hardly realized for the vast majority of pulsating white dwarfs, as period by period comparisons between observed pulsation modes and those calculated for stellar models rarely yield a unique solution. So common problems are the ambiguous geometry of any given pulsation mode, either because you don't know which sequence of overlapping spherical degree overtones you're observing, or because you can't identify the central component of rotationally split multiplets. If you saw Sumantha's talk last session, last meeting, then hopefully these patterns may sound familiar to you. But these ambiguities can cause some problems comparing the models to data. I think the splitting ambiguity is particularly concerning because we're getting to the point with space-based data, we can pin down periods to the microseconds, but this introduces extrinsic uncertainties of order tens of seconds that are often not able to be accounted for simply. I guess furthermore, to resolve features of the interior structure, you really need a dense grid of models, but the high dimensionality of the problem makes this computationally impractical. So I'll show you a model of many millions of, a grid of many millions of models in a bit. I consider that to be quite sparse for this type of challenge. So I'm going to get to a new seismic method in a bit here that I've developed for circumventing these challenges, and which in turn I hope will be a powerful tool for mitigating them in the future. But first I want to take you quickly through the analysis of the TESS light curve of a pulsating helium-atmosphere white dwarf. This one, WD 0158-160, that I used my open source frequency analysis Python package Pyriad to do. This package aims to provide much of the functionality of the legacy software tool Period 04, but for the modern astronomy workflow. Some of you may find this useful for your own work. So I'm showing here the light curve of this star from test sector 3, along with its Lomb-Scargill periodogram. You can't pick out these pulsational variations by eye from the light curve. It's too noisy, but the signals stand out very clearly above the noise in the periodogram. We can simply read off the amplitudes and frequencies of these different signals. But Pyriad is not just for displaying the data, it's made to fit them with the pre-whitening algorithm. This is an iterative procedure, the first step of which is to identify the most significant signal, which is automatically highlighted with this black dot here. With the click of a button, this gets added to our model, and the best fit of the sinusoid with this amplitude and frequency is obtained and displayed over the light curve. Now, it's such a high frequency signal here that it just looks like a big red band, but I'll zoom in a bit to show some more detail. The periodogram updates to display the periodogram of the residuals in blue and the periodogram of the current model in green, so you can quickly see which signals are in the model and what still needs to be fit. The steps for selecting the next most significant signal and then refining the multi-sinusoid fit is repeated here once and twice. And then we have to be a bit more careful about these next signals. They don't represent independent pulsation modes. They have these arithmetic relationships to the modes we've already fit. These show up from a response of the star to the pulsations, causing the brightness variations not to be simply sinusoidal. These aren't independent pulsation modes. And so we want to make sure we identify them as the so-called combination frequencies and fit them as such and exclude them from comparisons with the models. Pyriad allows us to fit combination frequencies, enforcing these arithmetic relationships, which can improve our constraints on the individual pulsation frequencies involved while still noting that distinction. So we fit these combination frequencies as well and continue pre-whitening until all of these signals are included in our model. I'll zoom in here on one day of data so you can see in better detail maybe how this star is varying underneath the photometric noise. Consider that with just one night of telescope time, you could hope to maybe observe only a quarter to half of this. So from the ground, it's very difficult to resolve these different pulsation signals. And if you are observing over multiple nights from a single site, the daytime gaps can cause a lot of confusion about what signals are real in a ground-based data set. So TESS is really giving us outstanding data on this and many other pulsating white dwarf stars. So we end up with a table of 9 independent pulsation signals and 10 combination frequencies. The frequencies listed here are in units of microhertz, and typical uncertainties are on the order of hundreds of microhertz from a single test sector. And This table view for the frequency solution in Pyriot allows you to modify values manually or hold any frequency amplitude phase fixed. That can be helpful for imposing external constraints if you have any. So this is this new tool I've been working on for time series analysis of astronomical data and how it's used to fit this light curve of a pulsating white dwarf. Just note that this package is under construction. In particular, I plan to update it for compatibility with Light Curve 2.0 later this month. So please update it often. Let me know if it gives you any trouble or you have any feature requests. But in terms of white dwarf pulsation spectra, this one is pretty rich. It's got relatively many signals, which is why we chose to analyze it for a first light paper from the TESS Asteroseismic Science Consortium Working Group on Pulsating White Dwarfs. I mentioned that comparing pulsation periods to model grids directly is fraught with challenges. So we have to start with trying to identify the asymptotic mean period spacing of modes of the same spherical degree. Here I've shown the periodogram in period space rather than frequency, and you can see that there's a bit of a common spacing between signals here. And there are various tests that can be used to detect what that spacing might be, which here 3 different ones show spacings of around 38 seconds, which is consistent with the overtone spacing of L equals 1 modes. We can fit a line through these periods and get a best fit spacing of 38.1 seconds. I've mentioned that we don't usually know which rotational component we're observing, and this is no exception. We don't see a lot of clear splittings here, but we do have some indication of a small splitting here. So so in order to incorporate this uncertainty about which modes are the central components of multiplets, I've run some simulations assuming different mode identifications for each of these signals and propagate that error through for an uncertainty of 1.0 seconds on this mean period spacing. Now we go in this paper to show that 2 contributed seismic analyses, one from the Argentinian group in La Plata using evolutionary stellar models, and one from the Texas group using structural models, both find stellar models with similar parameters to best match the observed pulsations, and they use spectroscopic parameters to reduce some degeneracies, but no unique seismic solution is reported in this work. The new developments I want to share now have been made with the help of Agnes Bischoff-Kim, who computed a grid of over 3 million models with the white dwarf evolutionary code WDEC for this work. We vary the 2 global parameters of effective temperature and mass, as well as structural parameters that most affect the mode periods, the relative mass of the envelope and helium layer, and 3 parameters that vary the shape of this parameterized core profile. So the mean period spacing is computed for all of these models, and allowing for flexibility for the structure, each combination of mass and effective temperature, such as this is for 0.6 solar masses, 25,500 Kelvin, corresponds to a distribution of period spacings, as you see here. We characterize these by their means and standard deviations, basically approximating the distribution as a Gaussian. And then we can make comparisons to the measured mean period spacing of 38.1 plus or minus 1 seconds in green here. So the comparison accounts for uncertainty on the internal structure of the star, because we're looking at this distribution of model periods, as well as the uncertainty on the rotationally split components because of how we fit this based on a bunch of simulations of the data. And the powerful thing about mean period spacings is that they vary monotonically across the mass effective temperature space. So here the blue dots show the sampling of the original grid, but the interpolated mean period spacing contours are smooth and reliable. And in the background, I've color-coded what that spread in mean period spacings looks like for each of these points. Evaluating the likelihood that the measured mean period spacing matches these models reveals a swath of agreement through the parameter space. This is often the best we can do for white dwarf asteroseismology, depending on the modes that we have available. And often the spectroscopic effective temperatures are used to further restrict the solution space, but recall that these are potentially biased measurements. And so I want to show that we can do better here by using information from Gaia instead, and that's because we can compute reliable absolute magnitudes based on parallax distances. Similar to before, here's the distribution of radii corresponding to this point in that mass effective temperature space. Because the effective temperature is the same for all of these, we can convert these to absolute G-band magnitudes using synthetic photometry models from the Montreal group. Again, we represent this with a Gaussian and compare with the measured G-band magnitude scaled by the distance modulus. Here it's not particularly close. We do need to treat systematic extinction when making this comparison. And though the star is quite close at 68 parsecs, different prescriptions suggest that extinction is between 0 and 0.014 magnitudes. So we adopt that range with a flat prior and we'll marginalize over it later. Absolute magnitude also varies monotonically across mass and effective temperature space. So we treat it the same as we did the mean period spacing, and comparing to the models gives us another swath of greatest likelihood here. So putting these contour maps side by side, we see the synergy of these two measurements. It's clear from the way the contours traverse the space in opposite directions. That means that for a given pair of measurements of absolute magnitude and mean period spacing, there's a unique solution for the global parameters of mass and effective temperature where these swaths overlap. So we can compute the combined likelihood function to obtain the first demonstration of this seismic technique framework. We really narrow in on a single solution here and even see a clear covariance between mass and effective temperatures that could be used in further analyses. Marginalizing in both dimensions yields these probability density functions for effective temperature with an uncertainty of 625 Kelvin and mass with an uncertainty of only 0.015 solar masses. So this has been just a first demonstration of this technique that can be applied to any pulsating white dwarf with an identifiable mean period spacing. This does require a rich pulsation spectrum, but there are some dozen or so good candidates that I intend to characterize in this way. The biggest strength is that it isn't very sensitive to radiative transfer physics modeling of the atmospheres like a spectroscopic technique. We're not so sensitive to specific line shapes, maybe slightly to equivalent widths, but we're also able to incorporate uncertainties from rotational splitting, uncertainty, extinction, in a quite straightforward way. For these reasons, I really think this method yields some of the most reliable white dwarf constraints, and the stars characterized in this way could serve as benchmarks for improving spectroscopic models and techniques or other methods of characterizing white dwarfs. The framework can naturally incorporate priors, such as a mass distribution. And these G magnitude and period spacing contours, these ones, are applicable to any DBVs. And we could compute similar things for other types of pulsating white dwarf, which has me thinking that we're on track to defining some seismic scaling relations for white dwarfs, which are commonly applied to other types of pulsating star. And finally, we've really narrowed down this parameter space from this entire DBV instability strip or most of the DBV instability strip to this very small region of relevance to this particular system, informing us where we need to compute finer grid of models in order to hopefully achieve the asteroseismic goal of resolving the interior structural profile of this or other richly pulsating white dwarfs. And with that, I want to thank you for tuning in.
We can't
Roberto,
hear you, Roberto.
I can't hear you.
Sorry, now you can hear me. Yes. So thank you again for your talk. The first question from Alejandra Romero.
Hi, Keaton. Really nice, really interesting. I have a few comments. From Gaia, I've noticed that when the stars are kind of blue, is the effective temperature, for instance, determinations have a lot of uncertainty because Gaia filters are kind of reddish. And I've noticed this, for instance, with Sirius B, which is a 20,000 something star. And since you're working with dBs in this case, do you think that could be a problem, or that happens to higher, bluer objects?
I'm not sure about that. When you're talking about the effective temperature from Gaia, so I'm not actually using an effective temperature determinant.
No, I know you're using magnitudes, but the thing is, when you derive parameters from Gaia filters, it kind of gives you a large uncertainty. I'm just saying because the magnitude doesn't seem to work that well, and. Yeah, maybe for Sirius B, for instance, what happened is that when you compute the log G value from the mass taken from the binary and the radius taken from the distance, it's very different to the spectroscopic value. And I was wondering if that is caused by Gaia filters or simply that spectroscopy doesn't seem to match distance.
I'm not sure about that particular case. That's the first I've heard of it, but I'm interested. Yeah.
Okay. No, because the uncertainties are it doesn't match. Okay, the log G from spectroscopy doesn't match the one when you use mass from the binary and the radius from the distance. That the way you compute it. So that's why I was asking.
Yeah. Be aware of. Yeah.
Okay, we can talk later. And another question is, you said that this works for rich pulsators. So how rich they have to be? What is the minimum period? Does this minimum value depends on if they are long periods, short periods? Because, for instance,
it does. The asymptotic regime is sort of these. In these lower frequency signals, and so yeah, we need to observe, some part of this sequence of evenly spaced periods in order to pin that down. In this case, like we had some signals supported by ground-based data down here. This isn't in the asymptotic regime. We left this out of the fit. So you really need some. Overtones larger than sort of, K is 7 or 8 maybe, right?
Yeah, because the shorter overtones usually are the ones that suffer from mode trapping, and you can have like less than half the mean period spacing.
Yeah.
Okay, that I was thinking because that will be a problem for I'm thinking about DAs, I don't work with DAs.
Yeah, there's not a whole lot.
Yeah, and the hot ones usually have short low overtone periods, like 2, 3, 4 at maximum, and they are short. So maybe this technique wouldn't work, or you think it?
Yeah, I think it really is only going to be applicable to a handful of stars that have enough high overtone periods.
Okay.
And yeah, it's a good point. I highlight this idea that maybe we could do better seismology if we focus the computations in this region. But yeah, like with this star, there's not a lot of low overtone modes. So maybe there's not a lot of potential to constrain the core in this particular, for this particular stuff.
Yeah, okay. Okay.
Yeah.
Okay.
Do the best we can.
No, exactly. Yes, you can do the best you can with the things you have. So perfect. Thank you. Thank you for your answer.
Okay, I will read one question from the chat from Frederick Hessman. Why not use the median and 5%, 9%, 95% limits for the mean period spacing, given the asymmetrical distribution? Looks like more consistent fit with the models.
Yeah.
TESS statistics? Question mark.
Yeah, that's a good question. Yeah, perhaps this Gaussian is not representing this distribution perfectly. Yeah, that's something worth considering. This is sort of an in prep project, but yes, I've been thinking about ways to maybe fit, incorporate this slight skewness to this distribution in.
Okay, I think there are a few more questions, but probably at this point it's better if we go to the breakout rooms and you can split with the speakers and discuss the questions that you have. So we stop recording now, and thank you again, everyone, for talking.